In this video, we're going to examine using serverless microservices for building a serverless application. We're going to do this by decomposing the wild rides monolithic application from our first video into separate microservices. We're also going to take a look at Serverless Framework serverless.yaml file. Our objectives in this video are to understand using serverless microservices to construct a serverless application, as well as to understand how to create and configure a serverless application with Serverless Framework. To accomplish these objectives, we'll 1. Deploy separate microservices to create the wild rides application, and 2. Examine the serverless YAML file for each service to understand how it is built. Let's start by taking a look at our application's architecture. Our previous architecture was a monolith. It coupled the front-end, back-end, and data layers together as a single application. We're now going to move from the monolith on the top to the microservices on the bottom. This is our new architecture. What was one deployable monolith is now 3 separate deployable microservices. The front-end, back-end, and data layers are now independent of one another. There's many reasons you might decide to refactor your monolith into microservices. Some, but not all, reasons might be at a certain scale or complexity, refactoring into smaller services can help make them easier to understand. Refactoring may also help align service ownership better with team or other organizational boundaries. Plus, there's also a 200 resource limit in CloudFormation. If your application grows to too many resources, you can't deploy. There's also practical educational benefit. The original serverless.yaml file was about 230 lines long. By breaking it up, it's easier for us to show how to use Serverless Framework to build common patterns such as REST APIs or to use S3 as a website host. Let's now go ahead and explore and deploy the new services. This is the Wild Rides Ride Fleet service. This service is responsible for managing the unicorn fleet. This is a RESTful web API that communicates with the database of unicorns. If this were a server-based service, you might picture this as a Python, Flask, or Ruby Rails application that fronts some sort of NoSQL database. The service currently consists of an AWS API gateway with a single endpoint. That endpoint triggers a Lambda function which will fetch a unicorn from DynamoDB. At a later date, we might add additional endpoints and functions to perform such actions as adding and removing unicorns from available service. This is the Wild Rides Ride Request project directory. A few contents of note in here. There's the serverless YAML. There's the requirements files for our Python dependencies. And finally, there's the handlers directory where we place all of our Lambda functions. Let's take a look at the AWS resources that compose the Ride Fleet service. I mentioned earlier there's an API gateway, Lambda function, and DynamoDB table, but there's also additional resources that are necessary. We need a Lambda permission resource that will allow API gateway to execute our function. Our function needs an IAM role that will allow it to fetch items from DynamoDB, and we also need a CloudWatch log group for function logs. Let's see how we create all this with Serverless Framework. Let's start by opening up the serverless YAML file. The service key is where we give the service a name. This value will be used to form the AWS CloudFormation stack name. The plugins section is where we define Serverless Framework plugins that we use. In our case, we use the Serverless Python Requirements plugin. This plugin bundles the Python requirements as defined in the requirements.txt file. The custom section is an optional section. In our case, we use it to define values that we might alter when we run Serverless Framework, or values that we expect to use at multiple points within this file. For example, the stage key defaults to the value dev, but we might set it via the command line or via the SLS stage environmental variable to prod if we were deploying to prod. Moving further down, we come to the provider section. This is where we define the cloud provider that we're deploying to. In our case, we're deploying to AWS and we're going to use the Python 3.6 runtime for AWS Lambda. Moving on, we reference the stage and profile values from the customs section previously. The environment key is where we can set environmental variables that will take effect on function runtime. In our case, we set a log level value that will be referenced by our function. Stack tags is where we set AWS resource tags that will be applied to all resources created by this stack. Lastly, IAM role statements is where we define all the permissions of the IAM role that will be applied to the AWS Lambda functions. We grant this role the ability to do DynamoDB put item, get item, and scan operations, and only on the unicorns table from this service. The resources section is where we define the DynamoDB table required by our system. We also have an AWS CloudFormation custom resource. This resource will execute a Lambda function during CloudFormation operations. We use this to initially populate our DynamoDB table with unicorns. Moving to the ends of the file, we have the output section. The output section lets us define information from the stack that we want to make available. In our case, we make available the URL endpoint to invoke our function via API gateway. We're now back at the functions section of this file. This service has two functions, request unicorn for requesting rides, and load table, which is called on deployment to load unicorns into DynamoDB. The request unicorn handler is the entry point of the Lambda function. We're telling Lambda to call the function named handler in the handler/getunicorn.py file. Remember the API gateway in the service that invokes this function? Where's that defined? In the event section, we define an HTTP event to trigger the function. The configuration in this file specifies that a GET request to the path/unicorn will trigger this. We've glossed over a bit of the configuration details in this file, but we'll cover these details in later videos. Now, let's go ahead and deploy this service. To begin, we need to install the Serverless Framework plugins. We type npm install. Once that's complete, we do sls deploy-v to do the deployment. And a few moments later, we've now deployed our service for managing the ride fleet. Now we move to the Wild Rides Request Ride service. This service is responsible for receiving ride requests and returning pickup information to the user. This is another RESTful web API consisting of an API gateway endpoint and a Lambda function. When a ride request is made to it, the service makes a web request to Wild Rides Ride Fleet for a unicorn and returns the information to the client. The serverless.yaml file for this service is pretty much like the Ride Fleet service. The file is easier to read because the service is really pretty simple. There's a Lambda function that's triggered by an API gateway event, and down below in the resources section, it only defines a single stack output with the value of the API gateway endpoint for the function. What makes this service notable is this question: how does the ride request service find the right fleet service so it can make requests? How are we going to do service discovery? Well, there's a number of ways we can accomplish this actually. To name a few, there are Serverless Framework can look up and reference CloudFormation stack output values. CloudFormation has a built-in import value function that can obtain values from other CloudFormation stacks. And there's also AWS Systems Manager Parameter Store. For our purpose, we're going to use Serverless Framework's CloudFormation lookup. We'll start in the Ride Fleet service. We have a stack output whose value is the API gateway endpoint that triggers the request unicorn function. Moving on to the ride request serverless YAML, we see request unicorn URL. Serverless Framework will query CloudFormation for the ride fleet service and get the value of the request unicorn URL output. Further down in the function section, see the request ride function's environment key. We set a variable in the function's runtime environment to the CloudFormation value. Now, here in our function's code, we query the environment for the request unicorn URL. Coming further down to the getUnicorn function, you see the URL we default to for requests is request unicorn URL. This is a very simple and easy way to find another service in your AWS environment. At a larger scale, we'd probably want to use AWS Systems Manager Parameter Store, but this is fine for now. Deploying this service is just like deploying the last service. You type npm install to install the serverless plugins. And once that's completed, SLS deploy-v. Finally, this is WildRide's website. This service is a static website hosted out of an S3 bucket. You may not be familiar with this capability of S3, but it can serve up static content such as HTML, images, and client-side JavaScript over HTTP. This service also creates a DNS record in an existing Route 53 DNS zone. This lets us give the site an easier to remember name than the default. This service is so different from the previous two services, so let's take a look at the configuration. The first thing to note in this service is there's no function section. There's no AWS Lambda functions at all. So what does this service consist of? Well, there's an S3 bucket, an S3 bucket policy that grants access to all the objects in the bucket, and a Route 53 record for DNS. How exactly does this service work? To begin, we've created an S3 bucket. The name of the bucket is a fully qualified DNS domain name. We upload all of our static web assets, like our HTML, images, and client-side JavaScript, to this bucket. Now we're in Route 53 where we manage our DNS zones and records. Our DNS zone name is dev.training.serverlessops.io. In that zone, we can see an A record. The name of that record is the same as the name of the S3 bucket that we just created. The record points to the S3 website endpoint for the region we created the bucket in. When a request is made to our website, DNS returns an IP address for the S3 website endpoint. An HTTP GET request is then made, and S3 will match the host name in the request to our bucket of the same name with our static assets. This is how we serve up our application front end via S3 using a custom DNS domain name. Now that we've seen how S3 site hosting works, how do we set up our S3 bucket and Route 53 DNS via Serverless Framework? To start, in the Customs section, define a bucket name. The name in our case consists of the service name, stage name, and the name of the Route 53 hosted zone. Then we go down to where we define the S3 bucket. We create a publicly readable bucket and give it the name defined earlier in the custom section. After that is the website configuration. We enable S3 site hosting by specifying the bucket object to be the index document of the site. Pay attention to the name of the S3 bucket resource. It's called static site, and this is going to come up again later. Come further down to the bucket policy. We want people to be able to access the contents of the bucket. To do that, we have a single policy statement. It lets anyone get any object from within the bucket. Finally, there's our DNS record. Let's start at the name property. The name of the record is derived from the CloudFormation ref function. It references the resource in our stack called static site, which is our S3 bucket. Then we set the record type. Below that, we configure an alias target. An alias target lets you reference another AWS resource, and Route 53 will handle resolving that target's value on its own. The DNS name is the S3 website URL as provided by AWS. The hosted zone ID is the Route 53 hosted zone where AWS manages the DNS name we specified. We got all this information from the AWS documentation, and a link to it is in the file's comments. Lastly, we specify the name of the hosted zone to create our record in. This value was defined earlier in the custom section. Before we can deploy this service, we need to tell it where the ride request endpoint is. To do that, let's go back to that service. Type SLS info-v to get the stack outputs. Down here in the outputs is the request ride URL value. Now we go back to the website service. Here we edit the file static.js config.js. There's an invoke URL key. There we will insert the request ride URL value. Now, Our static website knows where to make ride requests to. We're now ready to deploy the application's front end. We do an npm install and then sls deploy-v. Once finished, obtain the URL of the newly deployed website. Into your browser, enter the newly obtained URL. Here we go. This is your newly deployed Wild Rides. Set a pickup point, request a unicorn, and catch a ride. What we've just done is visited a website hosted in an S3 bucket. When we clicked Request Ride, we sent a request to the Ride Request service, which in turn sent a request to the Ride Fleet service, and we returned the pickup information to the client. You've now created an application composed of serverless microservices. Be sure to come back for our next video where we will continue to expand on this application.